All right. Looks like almost everybody is here. Still waiting on a couple of people, but that is a-okay. If you have any questions during the presentation, please feel free to post your questions in the Q&A section. I will definitely answer all of them at the end, if not during the presentation. And besides that, there's no need to raise your hand. I can't, unmute you, but we can chat back and forth. And there will unfortunately not be NABCEP credits for this training at this time. My email is going to be at the end of the presentation. If you have any direct questions you want to follow up with, sales, technical support, just presentation questions, I'd love to hear from you guys. So please stick around. And without further ado, today we're going to be talking about why the battery management system, also known as a BMS, matters, and how to understand the differences between different BMS functions in our different products. So to begin, we got a brief overview of our company and our history. Going to keep it real brief because I know most of you guys have seen this slide before. We were founded in 2010 as OES Energy. Our batteries are outliving their warranty, and we've been using LFP since the very beginning, back when other lithium batteries were seen as unsafe and fire hazards. We were out proving to the Department of Defense that lithium batteries could be safe enough to meet their application needs, and actually getting them tested independently by the Department of Defense at Aberdeen Proving Grounds. Expanded our product line. We're always thinking about you installers, always trying to make our product easier to install, and really meeting your needs as well as the needs of the customer, putting you two first. So we've put a lot of variety within our product line to meet those needs. And then we've relaunched as SimpliPhi Power, and now we're scaling up our manufacturing so we can get batteries to you now. We are widely known as a company that has batteries available quickly on shelves at distribution centers waiting to go out. And that's not standard across the line. I know we were contacted by several people last year who had, maybe a bigger name company that they had ordered from, and they had been back ordered for over a year and kind of were just told, we'll get to you when we get to you, and actually switched over to us because we had product just ready to go out the door. So that is one real strong suit of our manufacturing is we're always increasing volume and our lead times are short. So one thing that kind of relates to today's presentation around battery management systems is safety. And when I talk about safety, I always want to bring up UL listings. Now, UL listings are important and almost necessary nowadays for installations to be permitted. If you're adding a system to a customer's home in a residential area where it's going to be inspected, they're probably going to ask you if the products you're installing are UL listed. It might affect your ability to get permits. It might help you pass inspection. In a lot of counties in California and New York, 9540 is completely required, which means that the inverter and batteries must both be UL listed and tested together for their interoperability and compatibility. And 9540A is a growingly required UL certification that actually involves forcing the system into thermal runaway by adding external heat and just seeing how it reacts to that. So that is, we've got all of our products up to the latest UL listings and standards. They've all either passed or gotten full reports. For example, 9540A, there's not really like a pass or fail or a certification. You just do the testing and they give you a report. So that's something we have completed and we can provide to your AHJ if they need it. As far as our battery makeup, what's actually inside the steel case of our batteries is only lithium iron phosphate chemistry and only cylindrical form factor. This is across all of our products. Cylindrical cells, think about a AA battery shape. This is really sturdy. It's got short circuit protection built in, and it's going to last the longest and give you the best performance. When you look at a pouch cell, it's not going to last quite as long. It's got a little bit more flex to it, so it's not the best for larger applications or applications where there's a wide temperature range. If you're going from hot to cold, and mobile applications, I wouldn't recommend pouch cells there either because they're a bit more prone to puncture. We really see pouch cells mostly in laptops and maybe previously in cell phones. Prismatic cells are increasingly common among DIYers, as you'll see today. Some kind of easy ways to build your own battery. Prismatic cells are a little bit easier to throw together on your own. They don't require a spot welder necessarily. You can use bus bars to tie them together. And unfortunately, they're a bit more bulky though, so they take up more room in terms of, packing the biggest punch inside of the smallest package is definitely why we've gone towards cylindrical cells in our products. What is a battery management system? So for those who don't know, a battery management system, abbreviated as BMS, is really the brain of a deep cycle lithium battery. It's going to keep the battery from functioning outside of its specified parameters, and maybe low voltage, high voltage, maybe extreme short circuit current cutoffs, things like that. It's also going to monitor various environmental conditions, and in many cases, it's going to keep data on file. And in addition to that, one of the main functions of the BMS, especially in a lithium battery, is it's going to balance the cells. So as most of you know, lithium batteries have a very thin voltage operating range. So the BMS is going to, keep those cells balanced even when they're, a small voltage difference in a lithium cell can mean a big difference in state of charge. And the BMS is going to make sure they're all at the same voltage and state of charge. Instead of having your battery be limited by the weakest cell, your BMS is going to balance during charging and discharging. So we'll talk a little bit about how it does that. The main purpose of a BMS is really just to protect the battery from catastrophe and damage and ensure that it's got access to its full capacity during each cycle. A BMS is not necessarily required for any battery to work. For example, you hook up 4 lithium cells in series and you connect it to a 12-volt load. It's going to work. It's going to turn on the load, but it's not necessarily going to be safe, and it's not going to be optimized performance. So a lead acid battery definitely does not need a BMS, and often it's not cost effective to include one. However, it would actually benefit the battery performance wise if you were to include a BMS in a lithium battery, or excuse me, a lead acid battery. It's gonna, balance those cells, allow you to protect the battery from damage outside of its parameters, etc. Whereas a lithium battery, it can also operate without a BMS, but that's really not a good idea. It's not going to last very long, and it's not going to be very safe. You really don't want to operate lithium batteries even once outside of their necessary parameters. It can cause damage, with as little as one, abuse to those cells outside of their parameters can damage them. Whereas a lead acid battery can often handle a bit more abuse, and it's just not designed to last quite as long in the first place. Another super key function of a BMS within a lithium battery is to prevent thermal runaway. So as you know, lithium iron phosphate batteries, thermal runaway, not really a concern. However, in lithium, non-iron phosphate, so in lithium cobalt based batteries, thermal runaway is a huge concern. And the BMS is going to help, keep the battery cool and, turn fans on and off, turn cooling systems on and off, and keep the battery from being overcharged or, forced to a high voltage where thermal runaway could begin. All right. A general wiring diagram so you can understand where the BMS sits inside a battery pack and how it's wired. The BMS is basically going to cut the negative line in many cases. Now, it can be put in any way, but this is what I see the most often, is that it's going to interrupt the negative end of the circuit. So as you see here, the negative wires come off the cells, go through the BMS, and then out to the main negative output terminal. And they've got balance wires going to each cell pack. Many BMSs do have cell temperature probes. Some do not. And note that they're going to use some sort of device to open or close the circuit here on this negative end to, if it sees something it doesn't like outside its parameters, open circuit. If everything's good, it's going to close circuit. The BMS is not going to throttle or modify the current or voltage being provided to the battery. It's just going to open or close the circuit. So I think a lot of people imagine the BMS is just some unicorn that's going to clean up all the power you provide to the battery and make it nice and neat. It's not the case. A BMS is not, the only thing you need. You still have to design the system well and protect the batteries with proper programming, system design, and settings. And note that, often FETs are used to open the this and close this circuit very, very quickly. It happens extremely fast, faster than you can blink your eyes. And FETs cannot handle a super high voltage, and contactors can handle a bit of a higher voltage. So let's touch on the types of battery management systems. Analog battery management systems are probably the most popular. They do not have a user interface. They're programmed during manufacturing, if at all. They really rely on, hard values across hardware components like FETs, resistors, diodes. They don't have a controller or a brain with a bunch of logic, programmed into it. Excuse me, they are the brain. They don't have a controller though. They're not transmitting data to external devices. They're not communicating with charge controllers. They're not displaying their values on a digital interface. It's a very simple internal device, internal to a battery. Whereas a digital BMS can be used in tandem with an analog BMS. Some batteries may have both, and they are programmable. Maybe in the field, maybe you can even reprogram the BMS in the field. They'll take digital inputs and convert to electrical signals so that the battery will take action. So for example, you can program in, let's say, a low voltage cutoff maybe of 20 volts into your 24 volt BMS, let's say, and it will then take action instead of only relying on that value across a component. A battery with a digital BMS, again, it might have an analog BMS as a failsafe, as a backup. They can definitely work in tandem. Is there a system, I got a good question here from Eric, is there a system separate from the BMS that actively manages the balance of cells in a system? No, the BMS is actually what does this. You can, if you're creating a DIY battery, you can add balancers that only balance cells and are not a BMS. But I think that in general, the BMS will always balance the cells, so there's not a need for both. All right, Joe, we're going to get to your question in just a minute here. Hold off. Low voltage versus high voltage BMSs. This starts to explain how BMSs work more in depth, right? So like, why can't we put SimpliPhi products in series? For example, our 48 volt BMS is designed to handle a voltage of 48 volts and not 100 volts or two batteries in series. So for example, if you've got two batteries in series, let's say you've got 100 volts from two 48-volt batteries in series, and one of the batteries just gets too full and opens the circuit, it's going to then slam all 100 volts from that circuit onto the point where the BMS opened. That's going to have 100 volts right across that BMS. And in many cases, the BMS is just not designed with hardware components to handle that 100 volts. That is the case with PHI batteries. They cannot handle being put in series because they're only designed for the voltage of the battery. The BMS, what the device that opens the circuit is not designed to handle way more than that voltage. In a high voltage battery system, however, a stack controller is used. The stack controller is going to monitor each individual cell balancer or BMS within each individual battery pack. And the stack controller is the only device that would ever open or close the circuit. And therefore, it is designed to handle that full high voltage of the stack. Now, we're talking really high voltage here. I mean, these devices can go, we make a high voltage product that can go up to like 1400 volts DC. So this is a whole nother level and generally a way bigger size system. In general, now you know where a battery management system sits within the pack. Let's talk about why they're important. They not only do cell balancing, but let's talk about what cell balancing is. Passive cell balancing is one method you can balance cells. This is the most common method of cell balancing. So at the top of a charge cycle, if any cell is to finish charging before others, the BMS will close a resistive circuit surrounding that cell and actually just burn off the excess energy that the battery is trying to send to this cell, allowing it to continue charging other cell packs while this cell pack is stagnant and not charging any further. Now, this is a really small scale power dissipation. We're talking like 1/10 of an amp or so. So this is not a huge amount of power that you're dissipating. You may also, okay, let me back up here. A brand new battery, the cells are going to be extremely well balanced, made from the same manufacturer, all the same grade, perfectly balanced from the beginning of the battery when it's sold to you. And over time, they're going to degrade the same amount over time to within a very small degree of variation. This is all you need in the case of buying a first-hand grade A lithium battery. However, if you're building your own battery with, let's just say, used cells from some sort of e-bike, you may really need active cell balancing to prevent your battery from being limited by the weakest cell in the bank. So this is going to see, okay, cell pack 3 is full. I'm actually going to take energy into some sort of maybe capacitor or energy storage device and then shove it into a different cell pack. So taking energy from this battery and shoving it into this one so that it'll work at a much larger scale. We're talking maybe an amp. And this is going to, again, help you balance your cells faster so that if they are further out of balance to begin with, you aren't limited by that weakest cell charging quick, and then those other cells only being 2/3 full and having to stop charging as well. One thing to point out here is if a battery over time does get very out of balance, let's say it's not the highest grade battery being produced from the beginning, and the cells, unfortunately, regardless of how well the BMS can balance them, one of the cells becomes way too full. The BMS will actually sense the voltage of each individual cell pack And if one of the cell packs gets to a dangerously high voltage, the BMS will cut off charging, in most cases, to the entire battery. What happens here when your BMS opens the circuit, you want to avoid the BMS ever opening the circuit by programming and designing it properly. Because if a BMS does open the circuit, it can cause a very rapid increase in voltage in the system. It's because of a change in inductance, right? So Joe's pointed out that he's seen this in his system with non-SimpliPhi batteries. And what I wanted to point out here is the batteries are designed with the ability to handle very small voltage spikes from this exact reasons. They have some capacitance built into them. This is generally built into all batteries, but absolutely built into ours, that they can handle the BMS opening the circuit without causing such a fast voltage spike that it will actually damage the battery itself. So that capacitance built into the battery will kind of smooth the voltage spike, keep that from spiking so high so quickly. But in general, what you want to do is just avoid that by having a very well-balanced battery. And I hope that also answers Eric's question about individual cells within a cell pack becoming unbalanced. You know, again, it's really not going to happen with a grade A, well-manufactured battery.
Our PHI products, they come with a internal analog BMS only. So this is not going to communicate with other devices. It works very similarly to a lead acid battery. So this doesn't, this is really better suited for when you're replacing lead acid batteries. You have existing older equipment in there that you don't want to replace, and it doesn't have communications. The PHI battery is a very simple battery. You know, everything in it is contained internally. There's no communication wires to run. Another advantage here is that it can actually be programmed, it can be scaled up infinitely, so you can parallel as many PHI batteries as you care to. I've seen systems of over 100 PHI batteries in parallel. Some people even use this for commercial applications. I know it's uncommon to see low voltage in massive commercial applications, but we do see it from time to time because of the ease of installation here. Now, on the other hand, closed loop communications come with our SimpliPhi battery. It's the same internals with a more advanced and hardcore BMS. This is going to auto-populate the most important protection set points within the solar inverter. It's also going to, display to the user or customer the state of charge, voltage, and immediate charge and discharge amperage through the SolarX monitoring software through PowerView. Because of its communication with the inverter, you can actually size as little as one battery per SolarX or Sunny Island inverter, and it will communicate the charge and discharge rate it needs to be set at to the inverter. So it won't really allow itself to be overcharged or over discharged. Whereas, again, the PHI battery is not going to be able to do that. If you try to over discharge it, you may damage it. Here, the scaling up is limited, so you can have 75 batteries in a bank in parallel. The reason for this is because of the communications signal. It needs to be able to reach all 75 batteries. So this, I think, is a much better fit for grid-tied applications where you're putting in new equipment and you want a high level of monitoring, you want a high level of protection. Maybe you have an outdoor system going in cold weather environments. This is going to have much more protection against cold weather. It's got a low temperature disconnect, and even before that disconnect kicks in, it's going to ramp down the charge current that the inverter is allowing the inverter is providing the battery. Now, another product that many of you may not be familiar with is the high voltage system. So our high voltage stacks go actually up to 1400 volts DC nominal at this point. The stack controller is the one, again, opening and closing the BMS so that each of these individual series wired batteries are never seeing the full voltage of the system. It does have an individual cell interface within each battery. Right here on the left side, you can see these are actually basically just cell balancers and battery monitors. They're not necessarily a BMS within each battery. The brain of the system is definitely this stack controller up here. All right, so as we looked at an overview of our products, how do you choose the right BMS based on that? One thing to understand is, are you adding a battery to existing equipment? Again, older equipment without comms, your amplify is going to have basically no advantage there. So it's better to just stick with PHI and have that cost saving. If you want grid tied monitoring, you definitely want a amplify battery if you want a high level of state of charge reporting, a high level of monitoring. And another thing to consider is weather, right? So our PHI battery does not have cold temperature protection built in. So if you're planning to install in a freezing environment where you're not heating the batteries and you're not maybe taking them inside in the winter, then the SimpliPhi BMS is the one for you. Now, it can actually be used without communications, and it still has that cold temperature protection built in. I think that it works far better with communications, however, as the temperature protection is first going to ramp down the charge current from the inverter, and then finally does have that disconnect built in. And again, one other consideration is commercial and industrial, right? So often the amount of power and the type of power you need, maybe you need 480 volts and you need 500 kilowatts of power, that's going to be looking at a high voltage product. Can almost guarantee you. Before we answer the rest of the questions, I wanted to jump into our IQ program description. As an installer, becoming a member of our IQ program is going to allow your company to get more exposure through our customers. So we have people every day asking us who can install my battery bank. What we do is we refer them to this map that you see on your right, which shows where they can buy our products. They can buy them from you and you can install them. So this is going to give you more visibility to our customers. And as a distributor, you will be able to highlight more, your knowledge base and your ability to market with our products. So if you're looking to get more exposure and more SimpliPhi installs, you can apply right here, and I will get back to you as soon as possible. Cool, so I wanted to jump into the Q&A, and if you do have to jump, my email is here in case I didn't already get to your question, but I'm going to go ahead and answer the rest of the questions right now. Again, I'm so sorry, guys, about the audio dropout. Please let me know if there's anything that you missed, and I can go back and recover that. Is your LFP same size as Group 31 battery in 24 volt? I'm not sure about Group 31 batteries. We do have 24 volt batteries. For lithium iron phosphate battery systems, what is the viable temperature range for full charge and discharge characteristics? So full charge and discharge, you can do anywhere between freezing and 120 degrees Fahrenheit. So you should not charge your battery below freezing, but you can actually discharge it all the way down to -4 Fahrenheit. and all the way up to 140 degrees Fahrenheit. So it's got a very wide temperature window for our batteries specifically. Greetings from Canada. Will the slides be available after for reference? You should all automatically get a copy of the recording in case you weren't able to stay to the end. With the analog BMS, how does the system recognize temperature conditions in which batteries should not be charged or discharged? The PHI battery has a temperature sensor built in to completely disconnect the battery in absolute extreme high temperatures, but does not protect the battery from low temperature charging. This low temperature charging and discharging disconnect is built into the SimpliPhi BMS only. Are SimpliPhi systems available in temperature-controlled enclosures that allow year-round full charge and discharge in Northeast cold temperature climates? We have several customers using our SimpliPhi batteries outdoors in cold climates. We don't specifically provide a very insulated or heated cabinet. However, you can purchase heating pads and you can add insulating foam to the cabinet. We definitely have seen people doing that. However, I think, when you're looking at a harsh winter in like Maine or, eastern side of Canada, I really think that you're better off building a custom, very well insulated enclosure or keeping the batteries completely indoors. Keep in mind that our Boss cabinets and Express units are 9540 outdoor rated. They're super popular and I love them for outdoor installations, but they're a big metal box. It is a absolute heat sink and it's going to conduct heat or cold all the same. So I think that that's not the best device to use for a extreme climate that we're talking reaches, -10 Fahrenheit for a month at a time. In Alaska, you're going to want to build yourself a custom enclosure or put the batteries indoors. Is your LFP batteries 100 amp hours or do you have 200 amp hour batteries? We have several different models. I'd encourage you to check out the specs. We have a 48 volt, 75 amp hour, 3.8 kilowatt hour, or a 24 volt, 150 amp hour battery as well. How are the batteries holding up in UPS applications, 15-minute discharge cycle and 100 kilowatts or greater? Yeah, we really don't make products designed to discharge fully in 15 minutes. You'd want to look at our high output products or our high voltage products if you need 480 volts or an extremely high output discharge. Okay, it looks like I may have cut out during the analog and digital BMS explanation. I don't see any other new questions. So if that is everything, I'm going to actually rewind and go back through the analog and digital BMS explanations. All right. Thanks for bearing with me, everyone. Now back to analog BMSs. They do not have a user interface. They're made up of, standard hardware like FETs, resistors, and diodes. They're not going to have a controller that's programmed, with logic. Their performance is just going to be based on electrical signals and values across those hardware components. It's not going to communicate with other devices to, interact in terms of a high level of intelligence, data monitoring, or protection. Whereas a digital BMS is able to actually operate in tandem with a analog BMS. Sometimes a battery can have both of those. A digital BMS is programmable, and it may also be programmable in the field in some cases, but not always. A digital BMS is going to take digital inputs, right, from a computer screen, a value like a 1 or a 2, and it's going to convert that to logic and signals to take actions. It might not, however, transmit data. However, it can sometimes transmit data. For example, our SimpliPhi BMS transmits data to the SolArc. The SolArc is going to then show it to the user on its LCD screen or on its PowerView monitoring software. So often batteries with the digital interface are going to have an analog BMS as a failsafe. Again, they can work in tandem. In case I missed this, I'm going to go back through low versus high voltage as well. So a SimpliPhi battery cannot be put in series as far as our Phi and SimpliPhi products. They're really only designed for parallel connections. The reason for this is the device inside the BMS, like a FET or a contactor, in this case with the Phi and SimpliPhi batteries, it's not designed to handle more voltage than the battery. So if you've got 50 volts inside a battery and that opens circuit in the BMS sees 50 volts and that is totally fine. If you've got two 50-volt batteries in series and you've got 100 volts and the BMS opens circuit and sees 100 volts across that component used to open the circuit, that's going to damage the BMS if it's not able to handle that. So you have to be sure that the device used to open the circuit is able to handle that full voltage. For example, let's say your inverter is charging the batteries at 100 volts. You've got 100 volts going to the battery bank in series, and that BMS open circuit, it's still going to see that 100 volts right there on both ends of the BMS. However, a high voltage product, for example, you often are going to have a stack controller. The stack controller is the only device that would ever open the circuit. Each individual battery does not have a BMS, but a BMS that can open the circuit fully within each battery. It's only going to have a cell measuring device, balancing device, maybe monitoring within each cell pack and battery pack, but it's not going to have a BMS until you get to the very top of the stack. And that stack controller is the BMS. It can handle the full voltage that you're giving to it. That is how you get around, a BMS in high voltage scenarios. I think my audio cut back in here. Let me know, did I miss this as well? Should I go back through cell balancing? All right, looks like my audio was fine here. So I'm just going to answer the remaining questions. Does the SimpliPhi battery have both analog and digital BMS systems? Yes, it does. Is Phi using a digital BMS? No, the Phi battery is only using an analog internal BMS. It's only analog. There is no user interface with the Phi battery. Is there a limit to the number of 48-volt batteries that can be paralleled for capacity? So if you're using Phi batteries, You can parallel as many as you need. I have seen over 100 batteries in parallel when it comes to Phi. With SimpliPhi, you can parallel up to 75 because you need to make sure the communications line is able to transmit signal all the way to the end of that line. So based on the communications need, you can only parallel 75 SimpliPhi batteries, which is still, quite frankly, a whole lot of batteries. Looks like that's all the questions I have today, guys. Thanks for sticking around to the end. Thank you for bearing with me during my audio cutout, and I will see you next time. Don't forget to email me with any questions at training@simpliphipower.com. Have a good one.